This video will be an introduction to the ideas of momentum and impulse. So in a previous chapter, as we talked about work and energy, we related force and the work done. We re-expressed Newton's second law as an integral and showed that the total work done, the net work done, equaled the change in kinetic energy. We're going to look at something similar here, except we're going to relate a different quantity called impulse to the momentum of an object. So we're going to re-express Newton's second law, F equals ma, in an integral form, but now we're going to be looking at the force acting over a certain time as opposed to force acting over a certain distance, which was work. The definition of acceleration is dv dt. It's the derivative of velocity with respect to time. Newton's second law says that the net force equals mass times acceleration. So that would be m times dv dt. And then if the mass is constant, that's the derivative with respect to time of the quantity mv. And so we're going to define that quantity mv as the linear momentum of the particle. The linear momentum of a particle of mass m moving with a velocity v, it's a vector, and it's the product of the mass and velocity. The momentum vector equals the mass times the velocity vector. This vector equation says that this momentum vector and this velocity vector must point in the exact same direction. If the velocity is in the positive x direction, the momentum is in the positive x direction. If the velocity makes a 40-degree angle with the positive x-axis, then the momentum vector makes a 40-degree angle with the positive x-axis. The momentum vector and the velocity vector must be in the same direction. So momentum is a vector. It has a magnitude. The magnitude is m times v, and the direction. Again, the direction is the same as the velocity vector. So the momentum of a car driving north at 20 meters per second is not the same as the momentum of the same car driving east at the same speed. North and east are not the same direction. A ball thrown by a major league pitcher will have a greater momentum than the same ball thrown by a child because the speed is greater. Momentum has to do with the mass, and it has to do with the velocity of the object. The greater the velocity, the greater the momentum. A large truck, an 18-wheeler going at 65 miles per hour, will have a greater momentum than a smaller car moving at the same speed because the mass of the truck is greater. So momentum depends on mass, and it depends on how fast something's going. The units of momentum are kilogram meters per second. They're not given their own unit. Momentum is expressed in kilogram meters per second. Because momentum is a vector, we can talk about it in terms of components. The x component of the momentum will be related to the x component of the velocity. The y component of the momentum is related to the y component of the velocity. The z component of the momentum equals the mass times the z component of the velocity. So we can look at the components of the momentum vectors and relate them to the components of the velocity vectors. So Newton's second law can actually be written in terms of momentum. Newton's second law, this is actually a more general version of Newton's second law. The net force acting on a particle equals the rate of change of the momentum of the particle. The net force equals dp dt, the derivative of the momentum with respect to time. And the reason I said that this is a more general version of Newton's second law is because you can have situations where the mass of an object is changing. And so momentum is mass times velocity. And so if the mass is changing and the velocity is changing, you have to use the chain rule. It would be m times dv dt, which is usually what we've looked at for Newton's second law, but it would also equal v times dm dt. There would be that rate of change of the mass. And so that is a more general version of Newton's second law. If the mass is changing, then that rate of change of the mass also contributes to the net force. That comes up with the idea of rocket propulsion. When there's gas that's ejected out the back end, there's a force that's pushing the rocket forward, and you have to include that rate of change of the mass as part of your force. So again, this idea of Newton's second law in terms of momentum, it says that the net force acting on an object equals the derivative of the momentum with respect to time. And looking at this in terms of momentum, it shows that the more rapidly the momentum changes, the larger the force we need. If the momentum changes in a very short time, that takes a very large force. If the momentum changes in a longer time, if it happens more slowly, then that takes a smaller net force. Again, a gradual change in momentum will require less net force. And so you can have situations where the change in momentum is the same in two different cases. You get into a car accident and you're thrown forward. You have the option of either hitting an airbag or your face hitting the steering wheel. In both cases, your change in momentum is going to be the same. You are moving at whatever speed the car was going, and you are going to stop. When you hit the airbag, that change in momentum is more gradual, which means that there's a smaller force that acts on your face. When you hit the steering wheel, that's a more rapid change in momentum. It takes much less time for that momentum to change, and so that's a larger force that's acting on you. So again, a driver in a fast-moving car will have a large momentum. Momentum is the mass times velocity. Again, if the driver gets into a collision, the momentum goes to zero due to collision with the car parts, the steering wheel or the windshield. An airbag, it doesn't change how much the momentum changes by. It changes how much time it takes for the momentum to change. The momentum changes more gradually when you hit an airbag as opposed to hitting the steering wheel. So when you hit the airbag, it reduces the force that acts on the driver, and it reduces the possibility of injury. This same principle applies when you pack fragile objects in bubble wrap when you go to ship them. The idea is if it gets dropped, that padding is going to cause the momentum to change over a longer period of time, causing there to be a smaller force that acts on the fragile object inside.